Hello, and thank you for watching this webcast tutorial. I'm Michael DeLuca, Go-to-Market Manager for the Industrial Solutions Division in ON Semiconductor's Image Sensor Group, and I'm happy to talk to you today about some exciting imaging technology that enables image capture under a wide variety of different lighting conditions, going continuously from bright light down through dark shadows or from sunlight to starlight. Now, as you know, lighting is a critical component in capturing a good image. Professional photographers, for example, will use multiple lighting boxes when working in a studio in order to design the best lighting for their shot, whether they're looking for uniform illumination or developing a scene with very high contrast. They have full control over the lighting that they're using, and you can adjust the look of the final scene by moving a light in or out or up or down or adding additional lights to optimize the overall capture in the scene. It's actually a similar situation in industrial imaging, where, again, you often have good control over the placement and amount of lighting in a scene. Industrial robots, like the ones shown here, often have cameras associated with them that allow the robot to see the objects that they're picking up. And the lights for these machine vision cameras can be placed and optimized really wherever it's appropriate so that the robot can operate safely and efficiently. But things get a lot more complicated when the lighting in a scene cannot be controlled, like in an outdoor setting. On a bright sunny day, it might not be much of an issue because the light coming from the sun can often illuminate the entire scene. But when you go to nighttime in a situation where the lighting is not controlled, capturing an image that shows the entire scene can be more difficult. Now, this picture here is actually a good example. It's pretty clear that if you look in the middle, there's a gold-colored car under the street light. The car is next to a yellow building. There are two orange cones in front of the car. But what's going on in the foreground of the image? What's hiding in the shadows to the right or the left in the front of the picture? Is that a garbage bag on the right, or a person, or a box? You really can't tell from the picture that's captured here. Now, if you had full control of the lighting in the scene, you could just add a light in that corner and everything would be lit up clearly. But without that control, you need a camera that can look into those shadows while still being able to capture that bright part of the image. Here's another example taken not from a surveillance application, but from medical or scientific microscopy. This is an image of a cell as viewed under a microscope, where different structures in the cell have been tagged with chemicals so that they fluoresce in red or green or blue when the cell is illuminated under ultraviolet light. This fluorescence can be very, very weak. So to capture an image like this, again, you want a camera that can see into the shadows, or one here that's very sensitive to even the lowest levels of light. Now, in order to work under challenging imaging conditions like this, whether looking in the shadows of a dark alley or looking at a microscope, there really are two image sensor parameters that become really important. The first of these is sensitivity, which determines the lowest level of light that can be detected by the camera. Now, sensitivity really involves a number of different imaging parameters like read noise and responsivity, quantum efficiency, even the exposure time of the image capture. But together, they determine the lowest light level that can be seen by the camera. For a 30 frame a second image capture, a standard image sensor might have the sensitivity to capture down to a light level of single-digit lux, maybe somewhere between twilight and the light that's coming from a full moon on the scale that's shown here. But that a lot of times isn't enough for scenes like the ones that we're talking about here, where you really need to go down below this level into a sub-lux regime in order to be able to see deep into those shadows. The second key parameter is dynamic range, which is a measure of the range of the light levels that can be detected by the sensor at one time. In other words, once the sensor is configured to image under very low light, how bright can the scene go and still be properly recorded by the camera? Now, to capture an image in uncontrolled lighting conditions, like a dark alleyway at night, you need both sensitivity and dynamic range. The sensitivity to be able to see deep into the shadows, but dynamic range to extend the image capture all the way through to the brightest part of the scene without introducing imaging artifacts or losing image detail. At ON Semiconductor, our solution to this imaging problem is a new technology called Interline Transfer EMCCD. This combines two different technologies, Interline Transfer CCD and Electron Multiplication CCD, or EMCCD, in a way that preserves the best features of each. Interline Transfer CCD provides a high-performance base for the technology with global shutter or electronic shutter imaging that can capture moving objects with high image uniformity and without the introduction of motion artifacts. It also supports scalability to very high resolution so that the technology can be extended to multiple megapixel devices. EMCCD multiplies the signals coming from very low light scenes so they rise above the intrinsic noise floor of the device. This drives the effective read noise of the image sensor to sub-electron levels and enables detection of very low signals or very low light levels. When these two are combined, Interline Transfer EMCCD devices provide the flexibility that allows a single camera to image a scene where one portion of the scene is very dark, measured at sub-lux illumination levels, while a different part is brightly lit, all at the same time. Here's an example of what I'm talking about. Both of the images shown here were captured at a light level of 0.01 lux, which is like being outside on a clear night where the only light comes from a quarter moon. For the image on the left, you can see that the detail in the image is obscured by the background noise of the image sensor, which becomes prevalent under low light levels or under low light. But the Interline Transfer EMCCD image on the right is much cleaner. Even in this very low light condition, you can still see the detail in the image, even down to reading the words on the cover of the book. This high sensitivity is enabled by the electron multiplication register in the sensor, which amplifies the signals coming from these very low light levels so they rise above the noise floor of the device. Here's another example that shows how this high sensitivity now combines with wide dynamic range. The scene that we're looking at here has a bright light on the left side of the image while the right side drifts down into the shadows. If you use a standard CCD image sensor to capture the scene, the bright part on the left looks okay, but you can see that there's a lot of noise in the shadows on the right side of the image. A standard EMCCD image sensor would have no problem imaging the dark part of the scene since it can just amplify those light levels up so the signal levels up so they can be viewed cleanly. But now the bright light on the left side of the scene creates a problem. The light intensity there is so high that when the signals from there get to the electron multiplication output, it starts an overflow cascade that destroys the integrity of the image. You can turn up the gain on the EM register to try to see into the shadows, but before you get it high enough to see what's going on, the bright part of the image overflows. Interline Transfer EMCCD takes the best of both of these technologies and combines them using a standard CCD output for the bright parts of the image and an EMCCD output for the dark parts of the image. This extends the dynamic range available from the device beyond what's available from either of these technologies on their own, allowing the full information content of the scene to be captured in a single image. The way it works is through what we call an Intra-Scene switchable gain, which is the technology that allows the charge from individual pixels to be sent to either the standard CCD output or the electron multiplied output at a pixel by pixel level. It works like this. As part of the readout process for each frame, the charge from each pixel passes through a sensing node that allows the magnitude of the charge to be measured in a non-destructive manner. This information can be read by the camera control electronics to provide an initial measurement of the signal level for each individual pixel. It basically tags the pixel as being from the bright or the dark part of the scene. This information is then used to drive a switch in the sensor that routes charge packets to one of two outputs based on this charge level, on this tagging. Pixels with high charge levels that correspond to the bright parts of the image are routed to a standard CCD output for conversion to voltage. That's what's shown in the picture at the top. Pixels with low charge levels corresponding to the dark parts of the image go to the EMCCD output so that they get additional amplification before conversion to voltage. Then you take these two data sets and merge them together to generate the final image, an image that captures both the highlights and the very dark shadows of the scene, while avoiding the image artifacts that are associated with overflow of an EMCCD register. When they're combined in this manner, Interline Transfer EMCCD technology provides a combination of features that really is unmatched by any single imaging technology. The EM register enables exceptional low light imaging, capturing information in scenes that are illuminated at light levels well below 1 lux. The Interline Transfer CCD design provides high image uniformity as well as an architecture that's easily scalable to high resolution or to color imaging. And the Intra-Scene switchable gain that's incorporated into the devices provides wide linear dynamic range, up to 92 dB, or a range of 40,000 to 1. This set of features really makes the devices that are based on this technology an excellent match to light-starved applications such as surveillance, looking into that dark alleyway we talked about, or working with planes or drones for persistent surveillance in urban or rural settings, or in intelligent transportation systems, whether for a day-night camera or for toll collection, or medical imaging applications like ophthalmology, or a fluoroscopy modality like angiography or cardiology, or scientific microscopy. Really, any application where you need to be able to capture images with very low signal levels or extend that capture from low light through all the way to bright light. Today, ON Semiconductor provides a portfolio of products that use Interline Transfer EMCCD technology, and they're based on 4 main separate devices. These products range in resolution from 1080p, or 2 megapixels, up to 8 megapixels, and provide still or video capture at up to 30 frames a second, with options for different light sensitivities and camera integration options, allowing the most appropriate image sensor to be selected for a given application. Now, currently, we support 2 different pixel sizes in this portfolio, and pixel size is really very important in determining the overall sensitivity that's available from a device. All things being equal, big pixels are just better at capturing light than small pixels. So increasing the pixel size is one way to improve the performance of a device under low light. Now, nothing comes for free, of course, and using bigger pixels takes up more space. So what you're really doing is you're trading sensitivity for resolution in sensors that are the same physical size. The 2 images here show the importance of this pixel size on sensitivity. They were both taken under the same 0.1 lux imaging conditions, and the top image was taken with an 8 megapixel sensor using 5.5 micron pixels, while the bottom one was taken with a sensor that uses larger 7.4 micron pixels. These larger pixels are just better at capturing light. They're almost twice as big as the 5.5 micron pixels. That's why the bottom image is about twice as bright as the one on top. Those bigger pixels capture more of the light that's available in the scene, so they're better at capturing an image under really low light conditions. Now, this is a choice that customers can make. You can work with higher resolution or you can work with higher sensitivity, whichever is more appropriate. But when you're trying to capture every last photon, this trade for using larger pixels a lot of times is what makes sense. Another option available in this portfolio is to use a pixel design that enhances detection of near-infrared or long wavelength light. This is an improvement that we recently made in our standard Interline Transfer CCD portfolio, and now we're extending this into the Interline Transfer EMCCD portfolio as well. This new pixel design doubles the image sensor sensitivity for near-IR wavelengths like 850 nanometers, which can be really important in applications that are working in detecting near-infrared light. The 2 images here show this improvement. Both of the images were taken at night with an 850 nanometer illuminator, and they show the license plate and the front of a car. License plates in the US and in most of the world are designed to reflect near-infrared light, so they're a good target to use to show the performance of an image sensor that's working in this region. The additional brightness of the license plate in the lower image comes directly from this enhanced sensitivity available in the new pixel design. Everything else about the captures is exactly the same. And this enhancement is available today in the 5.5 micron pixel node. We look forward to rolling this out into the larger pixel in the future. We've also done some things in this portfolio to help camera manufacturers bring these products to market more easily. For example, the 2 products shown here, both 1080p devices, one with the standard pixel, the other with the enhanced near IR pixel, they're fully plug-in compatible with each other. That makes it really simple for a camera manufacturer to bring out a camera with the new pixel design. All they have to do is literally take the camera they have and plug the new sensor into it, and everything is all set. Now, another example of this work to try to simplify this integration is work that we've done to add a thermoelectric cooler directly into the package for these devices, which simplifies the work that camera manufacturers need to do to bring out a cooled camera. Cooling is really important to the performance of these, well, and other devices, to devices that are designed to capture under low light conditions, as the cooling helps to reduce the background noise coming from the sensor. The lower you can drive this noise, the easier it is to detect a small signal you're trying to see. We're integrating a thermoelectric cooler directly into the packages for these devices, which makes it much easier for camera manufacturers to develop a cooled camera design. This is an option in the portfolio, as some camera manufacturers have a lot of experience in this area. They want to be able to leverage that expertise and bring out their own cool designs. But for many camera manufacturers, this can be really important. Now, taken all together, there are now almost 30 different orderable parts that are available in our Interline Transfer EMCCD portfolio, with resolutions ranging from 1080p to 8 megapixels, with options for large pixels and enhanced near-infrared sensitivity, integrated cooling, color, monochrome, taped, sealed cover glass. We recognize that different applications for very low light imaging can have really different specific imaging needs, and that it's important to provide not just one or two options, but really a full portfolio of options to allow the best, the most appropriate image sensor to be identified and then matched to the needs of a specific application. Interline Transfer EMCCD technology really opens new doors for low-light imaging, providing the high sensitivity that's needed to image under sub-lux lighting conditions, as well as the flexibility and the high dynamic range that's required to extend that imaging all the way through to bright light. This new class of image sensor technologies, which we currently have implemented in a family of products with almost 30 different configurations for resolution, pixel size, color sensitivity, and packaging configurations, this is really enabling new options, new solutions for the most challenging low-light imaging applications. Thank you.